So we're going to be continuing in section 12.2, and we're going to start by talking about properties of quadrilaterals. So there's several different quadrilaterals that we have talked about, and in using all these properties, it's going to allow us to be able to look at some proofs of dealing with quadrilaterals. So the first type of quadrilateral that we're going to talk about is a trapezoid. Remember, this is a quadrilateral that has at least one pair of parallel sides. Now, might have more, but it has at least one pair. And when we have a set of parallel sides, consecutive angles, so that's going to be angles, for example, here and here, those angles are supplementary. Okay, so two consecutive angles between parallel sides are supplementary. Remember, supplementary means they add to be 180 degrees. Okay. If our quadrilateral is or trapezoid is an isosceles trapezoid, what it says is that we have a pair of a trapezoid with a pair of congruent base angles. That's going to be what we refer to as an isosceles trapezoid. Also, a side length is going to be congruent. Then we have these few properties. Each pair of base angles are congruent. So you can see that marked here with angle D and angle A, those two being congruent. And then also angle B and angle C, they are congruent as well. And then the sides that connect those different angles, those non-congruent angles, those side lengths are congruent. Okay? So pair of opposite sides are congruent. If the trapezoid has congruent diagonals, then it is considered to be isosceles. Now, that's a key one. If the diagonal that goes from point A to point C here, and the diagonal that goes from point B to point D, if they are congruent, then it is considered to be an isosceles trapezoid. Again, we'll use that coming up. The next one is a parallelogram. So we know that a parallelogram is a quadrilateral in which pair of opposite sides are parallel. So two sets of parallel sides. And you can see those. And so here are the properties of a parallelogram. It has all the properties of a trapezoid. Okay, so all those that we talked about with the trapezoid still apply here. So let me back up so you can see those. So consecutive angles are supplementary. Now notice it doesn't say of an isosceles trapezoid, it's just of a trapezoid. All right, so the properties of the trapezoid apply to this. Opposite sides are congruent. So we use that actually in example 6 that we saw in the last video. We use that property, that opposite sides are congruent. So again, in this case, you can see BD and AC, for example, are congruent. And then also DC and BA are also congruent. Okay. Also, opposite angles are congruent. So this angle and this angle, or this angle and that angle, they are congruent. And that should make some sense, because if we talk about the parallel lines cut by a transversal, and we know the alternate interior angles, we could easily identify one part of that angle and then the other part, and so together they'll have the same angle measurement. So opposite angles are congruent. Diagonals bisect each other. So again, if we take this diagonal from A to D and the diagonal from B to C, they bisect each other, which means that this length and this length are the same. and then that length and that length are also the same. Okay, so I've got a lot of markings there, but I want to make sure you see what this is talking about. And then a quadrilateral in which diagonals bisect each other is a parallelogram. So if we happen to see an example, which we will shortly, of where two diagonals bisect each other, well, that means that that has to be a parallelogram, without a doubt. Okay? Now, our next one is a rectangle, and we know a good bit about rectangles. So a rectangle has all the same properties of a parallelogram because it is, by definition, a parallelogram. All the angles are right angles, which I'm sure you know. A quadrilateral in which all the angles are right angles is a rectangle. So, for example, a square would be a rectangle because all the angles are right angles. The diagonals of a rectangle are congruent and bisect each other. So again, it's got the properties of a parallelogram, it's got the properties of a trapezoid, and so and it has, a rectangle specifically has the properties of an isosceles trapezoid because it fits in that definition as well, and so the diagonals are congruent and they bisect each other. So again, that one will be important in just a few minutes. A quadrilateral in which diagonals are congruent and bisect each other is a rectangle. So if your diagonals are congruent, so let's again back up here for a second. If they're congruent, wait, where to go? I'm sorry, if they bisect each other, so that's this property of a parallelogram. And then we said that they are congruent. So if they're congruent and bisect each other, then we do have a rectangle. So there's this statement that says diagonals of a rectangle are congruent and bisect each other. And so if we know the diagonals are congruent and bisect each other, then it must be a rectangle. The next one is a kite, and we don't deal with kites a whole lot in this class. But a kite is a quadrilateral with two adjacent sides congruent, and the other two sides are also congruent. And so you see a convex kite and a concave kite. We are primarily talking about a convex kite. And so in a convex kite, lines containing the diagonals are perpendicular to each other. And you can kind of picture that, I think, if you were to look at the diagonals going across here and going across here, they would meet and be perpendicular, form a right angle. A line containing one diagonal is a bisector of the other diagonal. Okay, so this one going across horizontally bisects the other diagonal. Okay, so that's what that says. It also says one diagonal bisects a non-consecutive angle. So your diagonal is going to bisect, in this case, angle C and then also angle A. It splits those both into equal angles. And then a quadrilateral in which the line containing one diagonal is the perpendicular bisector of the other diagonal is a kite. Again, not one that we're going to look at a whole lot in this class. Our next quadrilateral is a rhombus. It is a parallelogram with two adjacent sides that are congruent. So, in other words, all your side lengths are congruent. And so it also has some various properties. It has all the properties of a parallelogram and a kite. A quadrilateral in which all sides are congruent is a rhombus. That's what we just mentioned. The diagonals of a rhombus are perpendicular to and bisect each other. So if it's a rhombus, again, this diagonal from A to C and the one from B to D, it bisects each other and it forms a right angle. It's perpendicular. And then a quadrilateral in which the diagonals are perpendicular and bisect each other is a rhombus. So again, that's that if and only if statement where the diagonals of a rhombus are perpendicular and bisect each other. And so if you have a quadrilateral where the diagonals are perpendicular and bisect each other, it must be a rhombus. And then the last one is a square, and it is a rectangle with all sides congruent. So that means all sides and all angles are congruent. And so it has all the properties of a parallelogram, a rectangle, and a rhombus. Okay, so it kind of encompasses most of those properties that we have talked about. Because remember, a parallelogram also has the properties of a trapezoid, and a rectangle has different properties of parallelograms and trapezoids and things of that sort. And so every time we've added some of these in, a square has all of those properties. Because even like on a rhombus, it had the properties of a kite. Well, a square has properties of a kite, but it also has properties of a rhombus too. A rhombus is a rhombus with a right angle, or a rhombus with a right angle, is a square. So again, we know that. And so we want to jump in here to example number 7. This is going to be one of our proofs that we're going to look at. And we've got 2 of these that we're going to do in this section, just because I feel like we need to make sure that we know how to use these proofs, how to kind of walk our way through it. And this really will finish up chapter 12. And so just so you're kind of aware of what's coming, we will do a couple examples here. We're going to prove some things, and that's going to wrap us up for this chapter. So just be aware of that. So here's what we want to do in example number 7. We want to prove that a quadrilateral, so a 4-sided figure, in which diagonals are congruent and bisect each other, is a rectangle. Now, if you go back to our properties of a rectangle, get back there it is. We said that the diagonals of a rectangle are congruent and bisect each other, and we said a quadrilateral with diagonals that are congruent and bisect each other has to be a rectangle. What we're wanting to do, though, is we want to now prove that that is true. We want to prove that this is a true statement. So let's think about a sketch here, just kind of as an idea. So we have a quadrilateral, and we're told that the diagonals are congruent and they bisect each other. So this part and this part are congruent, and this part and this part are congruent. And because they are congruent and bisect each other, all of those pieces, we'll call this, let's just label this A, B, C, D. We'll label this point O. So based off just what we're told, AO is congruent to BO, which is congruent to DO, which is congruent to CO. If they are congruent and bisect each other, those diagonals, that each of those sides have to, or each of those segments have to be the same length. Okay, so now, if we're wanting to show that this has to be a rectangle, then we need to show that there's a 90-degree angle somewhere in this. Okay, So you can kind of, and I'll kind of walk you through this as we go, based on the fact that those links are the same. If the diagonals bisect each other, by our definition of a parallelogram, you have to have this side be parallel, and then also this side be parallel. So again, use my sketch here at the top. Well, if that is true, then this segment DB is a transversal, and AC is also a transversal. And so we can know about some angle measurement. So let me change our color here so we can kind of clearly mark this. So if this from D to B, this diagonal, is a transversal cutting two parallel lines, then this angle and this angle have to be the same. And then also this angle and this angle have to be the same. And you could do the same thing with the other sets. Now, in a parallelogram, it has all the properties of a trapezoid, right? And we said that the trapezoid, or in a trapezoid, consecutive angles are supplementary. Now, let's take this transversal idea and kind of go with it for a minute. We know that this angle and this angle have to be congruent because they are vertical angles. And we also know that this angle and this angle are congruent because they're vertical angles. Okay, so I hope you're following with me. Now, we also can know that this angle, put 3 marks for it, and this angle are congruent because they are alternate interior angles. And also, I'll just use a different color here. Also, this angle and this angle are congruent because they're alternate interior. Now, we still need to show that these angles, one of these angles is a 90-degree angle. Okay, so let's continue with what our slide shows because there's some better diagrams here. So we need to show that there's a right angle somewhere in this quadrilateral. So if we could show in triangle ABD, okay, so this triangle, if we could show that this angle is a right angle, or even this angle in this triangle, if we could show that as a right angle, then that would be helpful, right? And so if we kind of take apart what we have at this point, can we show that some triangles are congruent? Well, sure we can. So here's what we know for sure. Okay, we've already noticed these statements. Those are all true, but that may or may not really help us a lot. What we do know also, though, is that segment DC, that's the one at the bottom, is congruent to segment AB because we've identified this is a parallelogram, right? And so in a parallelogram, opposite sides are congruent. That's one of our properties. Which also means that AD is congruent to BC because, again, it's a parallelogram. And so when you look at this, if we can think about triangle, let's just do it this way. Let's do DBC. Ooh. So triangle DBC, that is this triangle here, this one big triangle. If I can show that that one is congruent to the one at the top above it, so again, let me change colors here. This one, so that would be triangle ABC. If I can show that those two triangles are congruent, then I can show that those two are right triangles, because trapezoids have to have supplementary consecutive angles, which means that this angle B and this angle C, the big angle, are 90-degree angles. Well, based on what we've talked about so far, we know that DC and AB are congruent. We also know that AD and BC are congruent, which that doesn't really help us a lot, but we know that BC and BC are congruent because they share this side. Okay, so you can see that. And so now I just need to show that there's an angle they have in common, or that they have the other side length in common. Well, again, based on what we've talked about, in the very beginning, we were told that the diagonals are congruent. And so BD, that segment, is congruent to AC. And so I have enough now, based off the side property, to show that these two triangles are congruent. And if that's the case, then angle C and angle B are both going to be 90-degree angles. And so therefore it has to be a rectangle. Now, I've got a lot of stuff written there, so let me kind of, again, walk you through what all the slide shows here. So if we can take BAD, okay, so you can see BAD, it's this triangle, and triangle CDA, so our book does it the opposite way of what I did it. So that's this triangle and this triangle. If we can show that they're those two are the same, then we're going to be able to show that there's two right angles. And so there's supplements. So these two angles here, BAD and CDA, these two angles are supplements because they're a parallelogram, which is also a trapezoid. And so triangle ABD, the one on the left, the one I've kind of marked in blue, and the other one have to be congruent because of side. Again, they share a side here. Their diagonals are congruent. That was given to us, right? And then BD and CA, so that's the two diagonals, they're congruent. And so you can easily see that all three sides have to be congruent. Because it's a parallelogram, this side and this side are congruent. And they share a side, so it is congruent. And then their diagonals, because again in our definition that was given to us, they're also congruent. But we can show those two are congruent, and since we have supplementary angles, if they're the same measure, 180 divided by 2 tells us it has to be 90. And so that is how that proof would go. Again, walking through it logically, I know this is a hard concept. I always tell people that teaching geometry is one of the hardest things that I do, because you teach people how to think. And that's hard to do, to guide your thought process to where it needs to go to get to our answer. But think about, okay, what all do I know? What are all these congruency pieces that we've talked about. How can I show that one triangle is equal to the other one? And how does that help me? So in this case, we needed to show that those two angles that were supplementary had to be the same. And so we showed that the triangle on the left and the triangle on the right, they had to be both right triangles, which gave us what we needed. Show that it's a rectangle. If you have questions about that, I can walk back through that with you if you'll let me know. We can do a Zoom session and be able to explain that in more detail as you need it. All right, so let's look at this one. This is going to be our last proof. This will kind of wrap us up. It says in the figure, triangle ABC is a right triangle, and segment CD is a median. Now, a median is a segment that goes from the vertex of one angle through the midpoint of its opposite side. Meaning that in this case, CD splits this bottom side into two equal parts. Okay, it goes to the midpoint. So, in the figure, if this is a right triangle, and it may not look like a right triangle to you, excuse me, the right angle is at angle C, so one at the top. So if CD is a median to the hypotenuse AB, we want to prove, so here's the key, prove that the median to the hypotenuse of the right triangle is half as long as the hypotenuse. Now, again, it may be helpful to kind of take this out to the side and draw a little sketch. So I'm going to try to redraw this figure so we can have a little more room here. So it says this is a right triangle. That's not really all that important for us at the moment. So this is A, C, B, and then the midpoint here is point D, which means that those two are equal. There's our segment. And so we're trying to show that CD, that median, is half the length of the hypotenuse. So in other words, 2 times CD, so 2 times the length of this segment CD, would need to equal the length of AB. That's what we're trying to show. So, how do we do that? Well, there could be a number of ways that you sort of approach it. The first thing that comes to my mind is that if CD is half the length, then let me extend this out this direction. And if I extend that out, then I can make another triangle here. And if I've extended this out where this side or this length, that CD, is congruent to this length, well, now all of a sudden I have created two diagonals that bisect each other. And based on the fact that a parallelogram says that your diagonals bisect each other, that tells me that this side and this side have to be parallel, and this side have to be parallel. So that's a good place to start, right? And so, since I have two sides that are both parallel, I really need to show that, and by the way, we know this is a right angle, right? Well, in a parallelogram, like we mentioned in our last example, this also must be a right angle because it has the properties of a trapezoid that says consecutive angles are supplementary. So it had to be 180. So if that's the case, then sort of like in our last example, if I can show that triangle ABC is congruent to triangle, make sure I mark the right one here, So we're doing, let's say ABC, and I want to show that triangle CA, we'll label this as E down here. So triangle, what did I say? ABC and CAE. If I can show that those two triangles are congruent, then I'm going to be in a pretty good place, because if I can just show that it's a rectangle, then based on our definition of a rectangle, their diagonals they bisect each other, but they also are congruent. And so there's where our key comes in, because if I can show that CE is congruent to AB, well, then I can show that CD is half of AB. Okay, so that's kind of where we're headed. So we know that triangle ABC is congruent because, or to triangle CAE, because you can do it with a number of ways. You could do side angle side. You could do angle side angle. That actually is pretty easy here, because if we know that AC is congruent to BE, and we know that let's see, BCA, so angle BCA is congruent to angle EAC. That's the two that I've got marked with right angles. If we know they're congruent, we've got a leg of a right angle. So we could do hypotenuse leg, would be maybe one way, but we're trying to show that other side's congruent. So we know that this side and this side's congruent. We know that this angle and this angle are congruent. And actually, instead of saying BE, we could say that AC is congruent to AC, because they share that side, right? And then we either need to show another angle or we need to show another side. And so the fact that we know we have a parallelogram, we know that we can find all the angle measurements within this triangle. And so we could show that, let me mark it with a different color here. We could show that this angle and this angle are congruent, which is also going to mean that let's see, this angle and this angle are congruent. And so by we could find this angle and this angle and this angle and so on. So we could figure out every angle measurement and figure out what all is congruent. So again, my diagram, my sketch may be a little confusing. So let me kind of show you what the slide here says. So show extending that out. That's what we did, right? And I'm going to try to not write on this just because I think the diagram here is a little easier to see. If you extend it out, then CD and now DE would have to be congruent. Okay, that's what, again, this side's congruent, this side's congruent, and those two we already knew were congruent. That guarantees it's a parallelogram. So that is parallel and this is parallel. So, because D is the midpoint of AB and midpoint of CE, it is a parallelogram, so we just mentioned, right? And since C is a right angle, then it's got to be a rectangle. And so I really was kind of taking you through a longer journey, but really that's enough, because our definition of a rectangle is that it's a parallelogram with a right angle, right? And so based on the fact that it is a rectangle, then that means that CE and AB, so again, both those diagonals, they're congruent. And so half of one of them would be equal to 2 times the other. And so this, so let me say, this part is going to be half of this length. Okay. And so that's what we see here. The diagonals of a rectangle are congruent. Again, CE and AB are congruent. Therefore, 2 times CD, which gives us CE, is the same thing as AB, or in other words, CD is half of AB. And that's what we were asked to prove in the beginning. We're trying to show that they are, that statement is a true statement. Again, a lot of ways you can do this. We could have found every angle measurement and showed through side, 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 or side, angle, side, or angle, angle, side, or any number of ways to show that all of those angles are congruent. I hope that as you are studying this section, you go through and make sure you really know those properties, because again, a rectangle has properties of a parallelogram, which also has properties of a trapezoid, and so on. So making sure you understand all those properties that go together, and it might be a good idea in your notes to write out the properties of each of these. Okay, so to say, well, the property of a square is all these things. Properties of kites, and properties of a rhombus, and properties of a rectangle, and a parallelogram, and a trapezoid, and write out all those. And then maybe for a rectangle, do the same thing, and for a parallelogram, and for a trapezoid, and for each of those figures. And that way, when you get ready to prove something, then you say, okay, well, here's my list. Here's what I'm trying to show. And so what can I use to get me there? Okay, again, I know this is a confusing topic. It always is. It is always something, even when I taught it in high school, that people always struggled with. And so if you have questions, again, please, please, please reach out. Let me know, and I'll try to answer those. Very last thing here in this section talks about congruence of quadrilaterals and other figures. And we're not going to go into a lot of detail here. Just wanted to kind of give you this statement. So one way to determine a quadrilateral is to give directions for drawing it. So we're not drawing anything. Section 3, which I was going to assign to you for homework, is strictly based on constructions and how to draw different things. And we took that out of section 12.1. I've taken it out of section 12.3, which is basically the whole section. So we're not going to do any kind of construction. But what I want to get to is this last statement. So I'll finish reading that. It says, start with the side and tell what angle to turn at the end of each side to draw the next side. And so you can imagine if you were drawing one angle, you get one angle drawn, you go to the next angle, next vertex, and you draw an angle, and so on. That's what it's referring to. And it says, based off of that, SASAS, so that side, angle, side, seems to be a valid congruence condition for quadrilaterals. So you got to have more than just 3 things, because you have more sides and more angles and all that. And so this condition can be proved by dividing a quadrilateral into triangles, which is what we just did, and using what we know about congruence of triangles. So when you're asked to prove something about a quadrilateral, it is always a great idea to start by taking that quadrilateral and dividing it into triangles, whether that's extending the median out like we did, or extending a side out, or whatever it may be, or maybe cutting it in half, or if you can take a